Hello and welcome back to Humans versus AI. This is video 12, and in this video we're going to continue to build out our PPO wrapper by adding a reward function, and we're going to talk about what that looks like and why it's very important. You know about this by now, but just a reminder, if you'd like access to the code, please do check out my Patreon account. Right, we're going to try and keep as brief as possible, so we're going to get straight into this. In the last video, we built out our PPO class, which is the wrapper around our game. We created the reset and we created the step function. We also created a placeholder for calculate reward down here, which I've now replaced with a full working version, which returned a placeholder value just so that we wouldn't break the code and we could still run it. So if you remember, step is basically one training iteration. And because we only want to train when a decision can be made by the machine, we have this loop which says the player can't be in transit whilst we move everything else forwards and make a decision. So this code won't get any further than here, won't get any further than this loop here if the player's in transit. So when the player stops, we know that the player is settled within a grid cell. Now that's really important. I've reminded you about this because it sets the scene for the reward function. So we know that the player, which is located by the player attribute current x and current y, we know that it is in the middle of a grid cell. We then, given that case, set the target position based on the action. The action, of course, coming from the step function itself, i.e. coming from the machine learning model, which means we've got a state, the game has moved to a stationary point when we can make a decision because the player isn't moving, and then we determine what the target position should be based on the action from the player, from the machine. Now that gives us a target X and target Y position. So if we go back to player class, you remember that they have a few variables, member variables, but two of them are current X and current Y, which is their current position just mentioned, and target X and target Y, which is where they're trying to go to. So again, this is very important, which is why I'm reminding you. So target X and target Y is now set by this method, which is a method from the game. If you recall, we have an instance of the game because when we initialize the PPO class, which we haven't done yet, but when we do in main, we have to pass it through an instance of the game app. So the game app will carry with it the methods that we need to be able to run the game from the PPO class. Okay, hopefully that's clear. So back to the point, we've got target X and target Y, we've got current X and current Y, we've got state, and then we calculate the reward. So essentially we've got where the player is, where the machine wants the player to go. So now we need to reward it for that decision. So now we're going to get into the meat of this, this video. So your reward shaping is critical in reinforcement learning. There is no parameter that's more important than getting this right. You may think that hyperparameter searching and optimizing the free parameters can make a big difference. It won't if your reward shaping is wrong. So it doesn't matter how much fine-tuning you do, the reward is really what will make a success or failure of what you're trying to do. And I did spend quite a bit of time creating this, even though it resolved eventually into something very simple, to get it to work. So the first piece of advice I'm going to give before I get into this code is always remember what the machine can see. Never lose track of that. In our case, the machine can see its observation, its state vector, which is a series of relative positions between the player and the energy, and a series of absolute distances from the player to the energy. That's its whole universe. And we've got to expect it to know that and then be able to improve its learning and its model based purely on a single number reward against the action that it takes based on its state. So that's a challenge. And so we've got to be very, very clear. The reward has to be really obvious. You can't expect a lot here. So what I'm going to do here is create a reward structure which favors the machine player moving in the direction of where there is greatest energy. And I'm going to use the term energy density to refer to that. So I'm going to quickly bring up a previous presentation that we did a few videos ago. This was a sneaky peek at what I'm referring to as the energy density reward landscape. This has been generated using the code that you've just seen, largely. And it gives you a nice rendering of what the reward landscape looks like for my game. Each energy point is radiating, effectively, an energy signature, where it has very high energy signature in its immediate locality, reducing as we get further from the energy exponentially down to very little, which is the blue areas. As a consequence, because the energy signature is cumulative, because multiple energy points can contribute to your energy signature, you get this clumping, this high red area close to where energy already exists. So this plot was created basically by pretending that the player was in each grid cell and recording what the energy looks like, or what I might call the energy density or energy signature looks like from each grid cell. So I basically move the player around all the grid cells, and then I plot what the energy looks like from the player's point of view if it were sitting in that in that grid cell. That's how I created that, and that's what we're going to try to create. Now, what's important is not what the energy density looks like. I mean, it helps us to visualize what's happening. The machine can't see this. We need the machine to implicitly learn this. All it can see is the relative positions of these dots and their absolute distances. So our reward structure is going to create this so that it learns this relationship. But it's going to not reward for a given position. It's going to reward, of course, for an intent. And it's very important to remember that. This rendering is not accounting for intent. It can't. We don't know what the intent was. What we're just saying is, based on a given position, what does the energy density look like? The intent is which way the player wants to move based on the model's output. So let's pretend, I mean, the green dot is the player, but let's pretend the player's here on the edge of this blue area. If the player wants to move, because the machine suggests it does through the action, in this direction, upwards, the reward density or the reward signature is going down in value. If that's the case, we need to penalize the player because it's going in the wrong direction of the general location of the energy. But if the player were to go, for example, left, it's climbing up the energy density, and therefore we need to reward it because the affirmative action it's taken requires rewarding. That's how reinforcement learning works. So what we're interested in doing is rewarding the player based on the movement it's about to make. So let's go back to the code then. To do so then, we need to first off create a variable for the player's current position, and we need to create a variable for the player's intended next position. So that's what these are. As you know, current x and current y are attributes of the player class. So that is the current x and current y for player 0. And the next one, target position, is the target x and target y for player 0. So it's where it wants to be. So the reward is going to be based on the difference between the energy distribution of where it is to where it's going to go. If the numbers get bigger, then it's clearly going in the right direction because it's heading towards energy generally, and therefore we need to reward it. If it's getting smaller, then it's moving away from the energy. Now we're just going to skip out this bit briefly, and we're going to go down to what I've literally just said, just there. The positive movement reward is ultimately what we want to produce, and it is simply the subtraction of the reward where the player is going to go from the reward where the player is currently. So that's all it is. The multiply by 7 is a constant that I've added just to fine-tune the model to make it perform nicely. It's arbitrary, and we'll talk about arbitrary constants a bit later. But yes, so there you go. You can see the bit I'm talking about. We're interested in the difference between the energy density where the player is to where it's going, because that's going to shape our reward. Okay, before we get on to any more of this code, let's talk about the bits above that I just skipped out. So cumulative reward next and cumulative reward current. How do we calculate the cumulative reward? So I mentioned back here that to create this plot, I basically pretended the player existed in each grid cell, and then recorded that and created this plot. Essentially, they are the cumulative reward at a given grid cell by taking into account the distance from every single energy point. that would be the energy at that point, energy density at that point, for every energy point on this grid. And that's true for every cell. So we just need to add them up. So we've got the sum function here, which is summing through every energy point and calculating the distance, exponential decay distance, from the player to that energy point and adding them all together. That's all it does. And that's what gives us cumulative reward current. Lambda decay is a constant. The value changes how sensitive we are, i.e. how quickly does the signature decay with distance. Do we want it to decay very slowly or very quickly? Again, it's somewhat arbitrary. It depends on how many energy points you've got per square or per grid. So yeah, again, this is specific to my game, so I won't get into the details, but it works. 0.2 just works. So that's for the current position, and then we do the same for the next position. Instead of doing the calculation based on the current player position, we do the calculation based on where the player is going to be. So we calculate the sum of all of the energy points based on exponential decay from that location relative to the player's position. So that's the current and that's the next, and taking the difference between them gives us the movement reward. So again, if the player is moving towards these big red blobs, they're going to be positively rewarded. If the player is moving away towards the blue, they're going to be negatively rewarded or penalized. That's the idea. Okay, so hopefully it's clear up to there what's happening. These two are quite important, but not necessary, but I like to use them. What this is doing is preventing very small numbers. With the exponential decay, you'll get numbers that are tiny, 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 and the model might struggle to know what to do and which way to go. So the player might just get lost over here and not have enough steer from the reward landscape to know generally which way to go. So what I do is I say, if the positive movement reward that we've just calculated is greater than 0 but less than 0.02, which is a bit arbitrary, but it's a very small number, then make it equal to 0.02, which means basically it can't be smaller than that. 0.02 is the smallest signature we're going to offer the model. And the same the other way. If it was a penalty and it was less than 0.02, we won't go below minus 0.02 because, again, we want the model to be able to move generally towards energy. We don't want it to get lost, basically. This will prevent it getting lost. So that's what that's for. So this is the really important part. This part, the exponential decay reward, is really the heart of this AI reward landscape. The other two bits are important, but not as important. The long journey penalty is there to subtract a reward of the same amount for every step, to dissuade the model from taking very long journeys. What can happen, and I don't have a video example of it, but what can happen is the player can move in a very beautiful and elegant way between the energy and go for the very furthest energy point, like this, to maximize its reward. And if you think about it, that makes perfect sense. Because as far as the game is concerned, as far as the machine is concerned, it gets the most reward per episode if it takes the longest possible journey across the reward landscape before it actually picks up the reward. Because when it picks up the reward, in this case when it actually collects the energy, it disappears from the map. So the whole landscape changes and it has to move on to the next one. So it's actually incentivized not to pick it up, which is absolute opposite of what we want. So what we can do is we can give it a penalty for making long journeys. And 0.06 is arbitrary again, but it works. And different numbers will work as well. And the other thing we can do, of course, is provide the machine with a significant reward if they've collected the energy. And that's what energy collection reward is. So by default, it's 0, because most of the time the player is not going to be collecting energy. But when it does, and it's detected through here, and I'll talk about this in just a minute, but before I do, when we have detected the player's collected energy, which let's assume that it has, the player will get 4 points for a reward of 4, which is very big, by the way. I mean, if we look at the energy density on this scale, and don't forget we're looking at the delta, the difference between the cells, normally we're talking increments of 0 point something for every step. So to get a single value of 4 is very big. And when eventually, and we will do this, we plot the reward landscape in time, not just in space, which we've shown here, you will see how the numbers compare to each other. I have the advantage because I've played with this with having rendering and I can see what the numbers are, but take my word for it at the moment, these numbers work, they're about the right scale, and we'll prove that when we render the plots, and you'll see. Okay, now talking about something I skipped over here, which is how do we know if the player has collected the energy? Actually a little bit more tricky than it might seem. So as you know, the player class has various state variables. If we go to player, we've got target position, current position, in transit, all of which have been very important to us. The other one is energy, which is how many energy has it collected. So if the player collects some energy, that's going to increment by 1. There's no other signal at the moment that tells the PPO wrapper player has just collected some energy. So what we do is we track the energy collected, which is this, and if player energy is bigger than it, then it has just collected the energy, and therefore we can reward it. Okay, if that does trigger, we'll set the player previous energy variable equal to player energy, so that again, when it loops around and it's moving around the grid, this doesn't trigger. So it's a way of capturing that the player energy has incremented up by 1. So there is something to add here if you're following along. Player previous energy is a new variable that we've added in this video. So if I go up, the first thing to note is I've added it to the reset method. That's new. It's the only thing that's new in here, but I've added it because when the episode ends, the player previous energy necessarily has to go to 0 because the player hasn't collected any energy when we start a new game. And then, of course, we have to define it or declare it as a variable here in the constructor, and we set it equal to 0. Okay, so that's where that is, and that's how we detect when energy is being collected. And when it does, we give the energy collection reward of 4. So what's coming back then from calculate reward is a number comprised of 3 additional components. The positive movement reward, which is incrementally increasing or decreasing with each step, depending on whether the player is moving generally towards energy or away from it. The long journey penalty, which is the same, it's minus 0.06 each time, and the energy collection reward, which is largely 0, except it goes to 4 when the player collects the energy. Without this, the model is incentivized not to actually collect the energy, but to loop around the outside of it, which is interesting. And you can have fun, by the way, if you are following along, when you do get this fully working, messing with this. You can have a lot of fun to see what it does. And there we go. That's our reward function. I won't go into any more detail. I don't wish to make this video very long, but hopefully you can clearly see now what we're trying to do. We're trying to reward the player for moving towards where most of the energy is by calculating the cumulative energy signature, where it is and where it's going to be. And that where it's going to be, of course, reflects the decision it's made and therefore is appropriate for the reward. And we will reward it. If it's moving towards energy, we give it a reward, which is, I should add, relative to how much it's moved towards the energy. So it's not a fixed number like long journey penalty is and energy collection reward is. It's based on the amount that it's moved. So obviously it can only move 1 grid cell at a time, but if you're moving towards a big clump of energy, there's a much bigger step between these two, for example, than there is between these two. So it's a non-linear, non-constant value, which should really encourage the player to move towards the energy, particularly the energy that it's close to. Okay, I should also say very briefly, the reason I've split it out into 3 components rather than just adding to a reward variable is so that later on we can plot them, each individual component, and see what's happening as the game progresses, which is very, very useful. Okay, we are very close now to training this. So stick with me, and in the next few videos we'll get a machine learning model training on our game, and we get to the really fun stuff. Thanks for watching, and I will see you in video 13.